Hello. Okay. All right, that almost broke. All right, welcome back to operating systems. So today, choose your own adventure. There's not that many people here. So what do we? So the choices are all on the slides, have all the topics on them. We can go over all really quick and I can talk and yap at you, or we could look at past midterms and we can see what's important about them or whatever. What do you want to do? Blast through everything, look at midterms. Midterms?
Yeah. If the midterms are similar, that is. Yeah. And probably.
I mean, I wrote them, so they're going to be similar.
And personally, can we go through like some of the earlier topics?
Earlier topics?
Yeah, like I'm already starting to forget some of them, like processes and page tables and stuff.
Processes and page tables. All right, so here, I'll go over the real quick. So let's go here. So just in case on these slides, examples of midterms I've read. So on my site, there's 353. It's essentially the exact same course. The midterm's the same length, 75 minutes. We can go through that one first. It should cover pretty much the same topics. There's also CS 111, which was the UCLA version of this. It is not a first-year course. Their course numbering is just really stupid. Don't ask me why. If it starts with a 1, it means it's a 3rd or 4th-year course. Don't ask me why. So that's similar, but theirs was 2 hours. Yours is 74 or 75 minutes. So that's the style I typically write, so we can go through them, see what's what. So here is the UCLA one. I'll skip it real quick. We can come back to it. All right, so here was 353. It's essentially the same course. It's by the same person, and it's the same length. So this will be fairly indicative of what you will have. In fact, your cover page will probably look exactly the same, because why would I rewrite it? All right, so the beginning of it had like a bunch of short answers to make sure that you paid attention during lectures, and should be one or up to 3 sentences. So first one was, what prevents a process from modifying their own page tables? So the only thing that should manage page tables is the kernel, right? So the kernel is the only thing that should manage page tables, and it does it in kernel mode. Your process runs in user mode, which does not have access to physical memory or anything like that. Your processes only use virtual memory, and the kernel does all the page mappings for you, right? Questions about that one, right? All right, then the follow-up was, well, say a process could modify its own page tables. What issues would that have? Well, if you can modify your own page tables, that means you can read all of memory. So there's nothing independent between processes. I can read, your banking application or whatever. You can just read anything. Nothing is private. There's no security, no nothing, right? Pretty bad. You could also modify each process's memory. So could you imagine you write your program and you try and write correctly and someone just randomly writes some new values? Your program's not going to work. It's going to be a disaster. Oh, yeah, the next one. Hey, let's see if we can leave this to the audience. So how can a process communicate using file descriptors if each process should be independent?
File descriptors are like public, right?
Not quite.
They're managed by the kernel.
They're managed by the kernel, and file descriptors are like essentially pointers to things, right?
Yeah.
So each process has its own independent file descriptors. That's true. But what the file descriptors represent can be shared between processes. So for instance, that's how you type in something in your shell, then you run your program, and when standard out outputs something, you actually see it in the exact same terminal. They're all sharing your terminal file descriptors, right? With a pipe, well, your pipes were sharing file descriptors. You created a pipe, got 2 file descriptors, you forked, so the new process got its own set of file descriptors that are independent, but they point to the same thing. So they might point to the same thing, but if one process, say, closed file descriptor 4, it wouldn't close file descriptor 4 in the other process. So they're independent in that way, but what the file descriptors represent isn't independent. Good? All right. So yeah, how can they communicate if they're independent? Well, they act as pointers. If you fork, you get copies. All right. I'll actually leave this to you. So if you have a newly created process, can you communicate with an existing process that's not directly related using pipes? No. Why no?
I thought pipes only exist between parents and children, no?
So the only way to share them is through forking, right?
Yeah.
So if the only way to share them is through forking, well, that already existing process would not have pipes open, and because it's unrelated, the unrelated process wouldn't have those same file descriptors either, so there'd be no way to have a pipe between them because they're.
The newly created process is not forced from the existing process?
So,
Unrelated, so I believe it's not.
so it's unrelated. So say, I don't know, well, init's the parent of everything. Oops. So unrelated means like unrelated directly. So init could have process 2 and then process 3. And then process 3 could create process 4. So we would say process 2 and process 4 are not directly related. Right, so if you are process 4 and you want, and process 2 already exists, no way to do it. Right, unless, in this case, well, if you go up to init and init created a pipe, then they could share it all, but then, you know, you typically don't go up to init. Init does not do that, so, yeah.
Will I get full points if I say what I said, like the thing about pipes only existing between parents and children?
So pipes only existing between parent and children isn't really true, because a parent and a child could create a pipe and not share it, right? They could create their own unique pipe. So it's that forking that you have to say. So, so forking's the important part here.
Thank you very much.
All right. Aside from calling exit or exit group to terminate a process, is there any other way to terminate it?
Return 0. Wait.
Does that count?
No. So return 0 is exit. Signal kill it. Yeah, everyone's favorite.
Oh, yeah.
So a process can be terminated by sending a signal. Sig kill will definitely do it. So remember in lab 2, so you had W if exited, and then at some point you realized that that might not be always true, and then you check W if terminated, or sorry, if signaled, right? So you can exit, or a signal can kill you. So that's like the type of questions you'll get that are related to your lab, but aren't like, here's your lab code. So that made sure if you did the lab, that should be easy because you had to have a case for that, right? All right, for scheduling processes, this is, your friend has a poor idea. All right, so your friend says that we should switch processes after they execute just a few instructions, so you have the lowest response time possible. Is your friend smart or not?
What is that overhead thing again?
Yeah, so context switching is going to take some time. Probably it's going to take more than a few instructions to implement a context switch. So if you just context switch after a few instructions, you'll probably spend a lot of your CPU time just context switching, aka not doing useful work, aka it's just overhead. So in this case, your friend is silly because most of your CPU time is just going to be wasted just moving registers around and swapping things, not actually doing any useful work. So you want your context switch to be like less than 1% of your overall execution time, something really, really small. All right, so short answer, not too bad, right? We're less scared?
No, I mean, to be honest, if it
What?
I mean, that's like I didn't review at all.
Yeah, you didn't review it all, so this is not bad for being completely cold.
If you say so, sir.
Go back to the short questions. Yeah, because actually a lot of them have quite a few points. How are you going to get 5 points out of 3 sentences?
Because the answer is long.
Yeah, the answer's pretty long, and it was, if it's 5 points and the answer's not that long, well, we only like subtracted points from everything wrong you said. So even if you said not much right, you could have even got like 3 points. Just don't say untrue things.
Oh, by the way, is there a no junk clause for this exam or no?
What do you mean?
Like no junk clause.
Like if you just have verbal diarrhea, will you get partial?
If you just write I don't know, you get 2%. That is the case for 3.5.
No. So for all these will be like, you should know something about it. It'll be like a process. If you just say, I don't know, then at least the way I write exams, I don't know shouldn't be valid. You should know something. It's like a process or something happens. Just say something. So yeah, the way things get marked is if you just like throw up on the page and try and display all your knowledge. My friend did that, and I hated when he did that because he just tried for part marks. And the way it gets graded here, everything you say that's wrong is essentially just a waste of everyone's time. So it's just minus every time you say something wrong. So don't write like 10 paragraphs for an answer that is like 3 sentences. So it just makes it longer to mark, and yeah. So here's another one. So you ask someone to write you some code that prints 1024 bytes from a file descriptor. They come back with 2 solutions. Here is our first solution. So we essentially have a for loop that executes 1024 times, does that many read system calls, and just prints out 1 byte at a time. And then the second solution is this one, is they just create a buffer, do a single read system call, and then print it all out in a for loop. So assuming that read and printf are always successful, what solution is better here?
The second one looks less sus.
Okay, what is the reason beside less sus?
Because like for first one you have to read 1024 times.
We cannot say definitively that read must be slow, but read is not really slow.
Can you not say definitively read is slow?
A file descriptor is not exactly a file on the disk.
So is read a function call?
No, it's a system.
Are system calls slow compared to functions?
I guess you can say that.
Yeah, yeah,
You can say that as a justification.
yeah, yep, yeah.
How does read work again? Because I somehow feel like for solution 1, it only reads like the very first byte like 1024 times. Or am I wrong?
No, so read will read 1 byte and then read the next byte and the next byte and the next byte. So if you read multiple times, you get it sequentially in order.
So basically every time read executes, it moves to the next byte?
Yeah,
Interesting.
yeah. So in this case, well, it was the simple system calls are relatively slower than function calls. So if you want things to go fast, do as few system calls as you can. So the first solution is terrible because it's like 1,000 system calls. Other one's only 1. So that's why. Not too complicated. The concept is just system calls slow.
But I mean, on the other hand, even if you don't know that system calls are slow, like calling the same function like 1024 times slow.
You're literally having the two instruction in one.
Yeah, but function calls can be fast. I don't know. Who's to say it doesn't get inlined if it's a function or something like that? That's another course. We won't worry about it. All right. Oh, here's a fun one. So this is based off you guys doing labs. So we have a child process. It opens this dev null file, which makes anything you write to it go to nowhere, so you never see it again. So it opens it, you get a file descriptor, and then we do a dupe2. Do people remember what dupe2 does?
Well, it copies the first one. What's the
Yeah, it
which
does.
one does it go again?
I think it comes in the first one. It doesn't point to the second.
So the second argument copies and then replaces.
We don't have a help sheet.
Yeah. Well, you have your own. So you're allowed one double-sided sheet of paper, whatever you want.
The cover page.
The what?
The cover page of the exam.
Oh, by the way, what are the HE requirements for the midterm?
Same as the final.
Interesting. Thank you.
See? Yours will be the same thing. Although I just put up a poll. This thing for must be handwritten, not mechanically reproduced, not true anymore. You can do whatever you want. You can try doing what I did for one of my courses, which didn't work out very well. I took all the lecture slides, made them super tiny, and printed everything on a page. Yeah, I did not do good on that exam.
You gotta bring a microscope.
Huh?
You gotta bring a microscope.
No, I could read it. I just didn't study before that. It just,
There's no time for it to even like print the CRS.
I could read it. It just, you have to go through like thousands of pages to find an answer. It didn't really work. All right, so for this, so it says first question here. You're trying to debug your program. You insert this print statement at line A, and you never see the output debugging in your terminal. Then you strace it, and you see that calls to open, dupe2 are successful, and also the write happens. Why do you not see debugging? I thought printf was supposed to go to your terminal.
Because you change the replaces the standard in terminal with the file descriptor, which will write nothing.
Yeah, so printf, well, printf just writes the standard out, which is file descriptor 1, and yeah, it doesn't matter, same thing. So this writes to file descriptor 1, and this dupe2 replaced file descriptor 1 to point to that black hole void. So we did a write to file descriptor 1, it's just we changed file descriptor 1 to point to something else. So that printf actually executed, but we never saw it because, well, we changed what standard out actually points to. Some of you probably encounter this in lab 2. Okay, so next question is, does line B execute?
If the previous line executes successfully, then it should.
Yeah, so do people remember what exec does?
It essentially replaces your process with another program.
Yeah, so it loads another program and replaces your process to start executing that instead. So if exec LP or exec VE or whatever is successful, then line B never executes because we're a different process. What's the case that line B will execute?
Line of program with the name ls, and we pass the two arguments into it.
Yeah.
And if it's successful, then exit will not execute.
Yeah, so if it's successful, you start, this process is executing ls now.
And this child ends.
No, it gets replaced. So it starts executing that program. And
Necessarily mean that this process ends.
no, So let's say process ID 101 is executing this function and it hits exec LP. Well, LS is going to have process ID 101 because it's exact same. It didn't change.
Where does this program go then?
This process gets replaced and starts
Doesn't mean, like this process ends or?
no. So the process only ends whenever it calls exit.
Oh, by process I think I meant the program. Yeah.
Program, same thing.
What?
But the program exists on a file, in a file on the disk, right? That's the
Yeah, so as part of the system call, right, the kernel is going to open that file. We saw that ELF file, like the whole description of it, and it's going to change this process's virtual memory to match that, load everything in the memory, and start executing that. It's essentially going to do like a make context on it, just with more steps. Okay. All right, here's the real fun one then. We can do this one. So, wait, can we see that? Probably not. Let's see the question. So, So this is a four-parter. So how many processes get created? What's the state of all of them? After process 100 terminates. Okay, so let's just go back to it. You tell me what this does. So let's say process 100, I think. Yeah. So say process 100 starts executing main. Tell me what's going to happen.
It forks.
And the child process will immediately exit.
It forks. Okay, so first it creates X, right? Assigns it to 1. Then it forks. So what's fork do?
Creates a child and returns
returns 0 and the child's ID.
So here on this corner, I'll write a family tree. So 100 is the current process. If it calls fork, it probably one, right? Like whoops. And let's just write, let's see what everyone's memory is too. So process 100, it created an X and assigned it to 1. All right, so when we fork, we create process 101. In process 101, will it have an X?
I
Wha-
think it will.
It should be because it's an exact copy of 100 at the time of the fork. So it will have an X. Its value is 1. So the only difference is the return value of fork, right? So in process 100, what's fork going to return?
What? Wait.
Yeah, in process 100, fork will return 101 and then create a variable called PID and assign 101 to that. And then what's 101 going to return from fork? Yeah,
Wait. Under what case? Oh, under what case does the fork return 0 again?
the one because it saves us a bit. Its value of PID.
0.
with a status of 0. So it's dead. Done. What's its current state? Will it have an x?
X is equal to 1 and PID is equal to 0.
Yeah, so it'll be an exact copy of process 100 at the time of the fork. So it will have an x equal to 1, and then a PID equal to 101.
Wait, why is it not 0?
Why would it be 0? So what process created process 102?
100?
Yep. And what was the value of PID in process 100?
101. But why did 101 get 1 get PID equal to 0 when it was first created?
Because it was a child.
Yeah, but isn't 102 also a child?
Yeah, but this PID was...
Which line are we on?
So we're currently... Whoops. I just erased it. We're currently here.
But does this form
Yeah, it's reassigned.
So basically, at line A, we
So we're at the... So we're going to reassign it, but right now, at the time of the fork, we go... The fork happens first, and then we assign it. So we're not done yet. We have to read our programs. Right? That's like the number one thing. People think programs just like do random things and don't go in order. So fork happens first, and then it assigns. So now fork returns, and we are reassigning PID. So now in process 100, what is the return value of fork, this fork?
102.
102, and then we reassign process 100. Oh, and the microphone's cutting out. It's been finicky. I will leave it there, and hopefully it's fine. It looks like it's fine. So it reassigns PID to 102, and then let's say in process 102, what would it get from fork? 0, so it would reassign PID equal to 0. So 102 is here. So now, which one do you want to execute next?
102.
102. So 102 executes next. It creates a variable called y and assigns 3 to it. So it has what? Whoops. It has y. Damn it. Y equal to 3. Yeah?
Yeah.
All right. Do we want to keep on executing 102?
Sure, why not?
Sure. All right. So is its PID equal to 0?
It is.
It is. So it will sleep for 3 seconds. So in this case, let's just assume that 100 executes because 3 seconds is like an eternity. So process 100 executes. It would create a Y.
What, sorry?
Process 100's going. So 102 is currently asleep for 3 seconds.
Sure.
So 100 went, created Y, and then,
Else
yeah, is PID equal to 0?
no.
Hopefully not. So else,
Update.
so it would change X, right? So which X does it change?
2.
Huh?
2.
Change it to
So does it change this one?
100. No.
Mm,
The other
oh,
one didn't.
no, okay. So, okay, so we're changing 100 to be 2. Does that also change this one to 2? I really want to change it to 2. Like that?
No.
No, right? They're independent.
Yeah.
All right, good. So let's say 100 keeps on executing. It changes Y from 3 to 4. Damn it. And, well, 4 is a long, so 3 seconds is a long time. Whoops. So it would hit this print. What would it print?
X is 2 and Y is 4.
So we see X is 2, Y is 4, and then it returns. What's returned from main the same as? Exiting. So process 100 has now exited with 0. So now we can go back and answer this question. So what is the state of all of PID's 100 children after PID terminates?
That makes 102 an orphan, right?
Yeah. Both of those is an orphan, but that's not the question. What's the question?
No, it's all of process 100's children. What state are they in?
They are all orphans.
Yeah, but 101 is also a zombie.
Yeah, so at the time it exits, well, 101 is an orphan,
And a zombie.
102 is an orphan, and yeah, 101 is also a zombie. So it's a zombie orphan. So we got a zombie orphan and an orphan orphan. So that's what the, so that's exactly what's said here. So it's a zombie orphan, and this one is just an orphan process. So that's what we said. 8 marks. Pretty good. Points, marks. Like, all right. What do you expect to happen after executing line C? Oh, yeah, so now we can continue executing.
Nothing.
So it wakes up, declares this, and calls wait.
After line C, will there ever be an after line C?
Yeah.
But 102 is still executing. It hasn't terminated yet.
Wait, what's the behavioral wait on the default step?
What?
Because 102 does not have a children to wait.
Yeah, that's the
102
problem.
can't wait for 101, can it? I don't think.
No,
Unless you like adopt it, like
No, so wait will wait for your direct child to terminate and the first one, right? In this case, does 102 have any children?
I don't think so.
That's an error. So wait will just be probably give you an error that says no children.
Oh, it wouldn't wait forever.
No, you get an error. You don't have any children. Kernel's smart. It knows you don't have a child. So you don't block forever. So here it says you would expect it to fail because the child process calls wait doesn't have any children. We should have checked for errors. Something I've told you a lot, and hopefully you may have learned. So it would have returned -1, set error no. Likely you didn't mean to wait in the child, so best to do that. Some students just changed this around and went like, whoops, not equal to 0 and wait, but then you're also changing around the print statements, which isn't great. You got a lot of part marks for that, but not total. All right, then we said show the output at line D when it's executed for all processes. So yeah, we're still going with 102. So 102 would wait, do nothing, come here, print. What does 102 print?
X is 1 and Y is 3.
X is 1, Y is 3.
By the way, sir, so an error in wait doesn't cause a runtime error and the program at all?
No. So wait returns -1, that's an error. We don't check for errors.
Ah, interesting.
We just ignore it.
Wait, so like, so the only thing we have to do is just checking for errors and handle it, like that's all we have to say in the question, or?
So in the question you said that you just have to know it didn't have any children. As long as you said wait does nothing because it doesn't have any children, that's fine.
Like, we don't have to actually change the code itself.
No. No, it just says what do you expect would happen.
I mean, afterwards there's another question.
Oh, without changing, is there anything you can do to improve it? Yeah, you can wait in the right one, just move the wait. That was also fine if you wanted to say that. So that,
I'll change the placement.
yeah, so it was supposed to just be like check for errors, but I was pretty lenient about it because some of them were like, I won't change the placement of wait, I'll change the if condition or I'll change everything around it. So yeah. All right, other stuff. So here, this will make you feel better. Scheduling question. So round robin, quantum length of 2. Everyone was bored to tears when I did in lecture because it was easy. So that will probably be a question for you guys to do. It'll be mostly free marks that will take you like some time.
What is burst time, by the way?
Huh?
What is burst time?
Burst time is like the amount of CPU time it wants to execute.
Interesting, thank you.
So in the lecture we use burst time, should be easy. So here's, yeah, so page table question. Here, I can delete all this. So what do you want to do in the last, 12 minutes? Want to do a page table question or go over stuff or what?
Page tables, I guess.
That's the page.
Page table, okay. So 2 hardest things are going to be page tables, virtual memory, and processes. So we did a process. Let's quickly do a page table. So this is an odd system. Generally, give you the page size. Again, you can bring a dumb calculator, but if you know your powers of 2, you can skip doing a whole bunch of calculation. So quick, 256 in powers of 2, what is it?
Wait, 8. Sorry, 8.
All right. 16-bit virtual address, page table entry size of 16 bytes. Powers of 2. 2 to the power of 4, right? So this system supports 32-bit physical, 16-bit virtual. It's a weird system. You'll definitely be. Behind that is all of the page table entries fit exactly on a page. So 2 to the 8 is our page size, and then 2 to the 4 is the page table entry size, and that says how many entries you can fit on a single page. So again, easy math like that. We should be able to do subtraction. It's 2 to the 4 or 16. So that's the number of page table entries you can fit on a single page. So next question was like, if we use multi-level page tables, how many levels of page tables we need? So if we remember our equation, so it should be on our cheat sheet if you can't think of it on the top of your head. It's the number of virtual bits minus offset bits divided by index bits. So what are the offset bits for? So what are the offset bits for? How many offset bits do I need?
Offset is for matching the virtual to the physical like addresses.
Yeah, it's for locating a memory entry within a page.
Yeah, so the offset bits are where you are within a page, right? So memory is byte addressable. So the number of offset bits I need is the number of bits I need to address every single byte on my page, right? Which is 2 to the 8. So
Wait, how do we know the offset bit again?
it's where you are within a page. So it's the page size.
So basically the page size is 16 in this case, or?
So the page size here is 256 bytes. And memory is byte addressable, so you need to be able to address every single byte.
So that'll be 8 bytes needed for.
8 bits.
Wait,
8 bits.
Okay.
So it's just this.
Oh, I see. Thank you.
So our offset bits are 8, and then from the question, our virtual bits right here is 16, and then the index bits are which entry in a page table that you are selecting. So here I can fit 16 entries in a page table, so I need 4 bits to select which entry in a page table, right? So that's the index bits.
That's not really how many levels we need. That's how many levels we possibly have.
For this system,
Less.
For this system, yeah, that's why we have the ceiling. So this is how many we need, minimum. So in this case, it's 8 divided by 4, which is a nice number, so it's 2. So we need 2 levels of page tables.
You even have only one entry on L2 and one on L1, like points to L0.
Yeah, but we can have a page table structure that we just have L1, and and in that case we'll have a few extra bits we can use for access. In this case, we're just literally filling into the brain.
But like then they won't be the same system, right? Like if
Yeah,
you have
this is all the bits are related to the page table entry size of 16 bytes. So that's where all the flags and everything are. Okay, let's go. Okay, so this is a screw up. So I said, is virtual address H1, 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 H1 valid? I tried to be funny here because I tried to make it say hi, 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 and didn't realize for some reason that H is not a valid hex character. So valid response was H isn't a hex character, you idiot, and that got you full marks. So what I was looking for is like, pretend H's were F's and I wasn't stupid. Well, each hex character is 4 bytes, so that address would be, what, 4 times 6, so it would be 24 bits, and we say we only have a 16-bit virtual address, so it'd be too big. Yeah.
Sorry, how do we know an index bit again?
Hmm?
How do we know the number of index bits?
So the number of index bits is related to how many page table entries you can fit on a single page, which is the first one, so it's this.
Offset bit. Right?
Yeah, so it's this one right here. So 4 bits. All right. So then it said, oh, okay, explain the steps you would need to translate the virtual address 1, 2, 3, 4 hex into physical address feed 0034. So if we take all the components of the address, so the reason the system's so weird is because it nicely fits to hex characters. So we needed 8 bits for an offset, which is 2 hex characters. So these hex characters right here are the offset. And then in each level of page table, we need 4 bits, so that's 1 hex character. So this is our L0 index, and this is our L1 index. So anyone want what would happen if I try to translate 1, 2, 3, 4 into address feed, assuming that it could do that translation, everything was valid.
Well, so you will first get the L1 and let's say
Yeah, so
the location of the L1 page table, that's a physical address. So you find the page table on the physical address.
yeah, so there,
That's the kernel, and then you get 1. Okay. 1 is the second entry here, and then you get a third, you get that page table, and then you get the third entry in that L0 page table, and then you get the content of that page table, and you combine it with the offset.
yeah, so when we're translating this address, well, we would have a root page table, right? What level would the root page table be? L1? We only have 2 levels here, so we only have level L1 and L0. So there would be a root L1 page table. So in order to translate this address, we would use that root L1 page table and then look at the entry at index what?
Sorry, what?
So in that L1 page table, when we're translating this address, what index would we look at for the page table entry?
1.
1. What's in the page table entry?
Something.
A page table entry, a pointer to a non-zero page table.
At index 2.
So in a page table entry, the important things in it is the physical page number and then some bits, like a valid bit, and then, well, if you, for lab 3, there was like a read, write, and a custom bit. So probably some bits and the physical page number. So the physical page number tells you where the L0 page table is, right? So we follow that to an L0 page table. What index do we look at in that page table? 2. And in that page table, what would have to be in that page table entry? Yeah, what physical page number would have to be there? Huh?
What?
The page that is mapped to 0x
Yeah, so it says this address, this virtual gets this physical address. So L0 should have our direct translation, right?
So 0
Yeah.
x feed for zeros.
Yes, not 4 zeros, it should just have this, right?
Oh.
Feed 0, 0, because that's the physical page number. Because the last 2 is just the offset. The offset doesn't change.
So we kind of concatenate them after the PPA.
Yeah.
So the physical page number is 24 bits. How did we store that in a 16 bits page table?
So the physical page number here is 24 bits. And our page table entry size is 16 bytes.
Oh.
So it's way bigger. Yeah, so then the last thing in the last minute says, for the system, could I use a smaller page table entry size? If so, well, that's where it relates. So like you said, the physical page number must be at least 24 bits. And if we only had a few flags, so assume we just have like a valid bit, we would need at least 25 bits. So we could actually just use 4 bytes for our page table entry. So that's 32 bits. I also accepted if you want to say like we use 10 bits for flags and then this couldn't get any smaller, that's fine. So just in this case, we can make the page table entry a little smaller, but even if we made the page table entry even smaller, do we see any benefits? No, because we still need 2 levels of page tables. So it might not be full, but we still have to go through 2 levels anyway, so it's not going to be any faster. Yep, real.
Those math where we do the powers and division and stuff.
Yeah, virtual to physical, it's just you replace you put in the physical page number and then use the same offset
Nice. Glad to hear. Thank you.
What if we have a TLB?
for this. Here, just remember, pulling for you, we're all in this together.